we live in this kind of weird, hyper-connected world, right? We want everything to be smarter, our power grids, our factories, even our nuclear power plants. And to make them smart, we need to connect them, we need data. But here's the terrifying part. Every single one of those connections is a potential doorway for a truly catastrophic cyber attack. So how do you get the information you need without leaving the front door wide open?
And yeah, that's the multi-billion-dollar question, isn't it? This isn't just some academic exercise. The demand for real-time data from these massive industrial systems is exploding. And at the exact same time, so are the cyber threats. The challenge is, how do you build a bridge for that data that is, by its very nature, a one-way street? A bridge that lets data out, but makes it physically impossible for an attack to get in. Okay, so to really get why this is such a big deal, you have to understand what we're actually talking about here. This isn't your company's email server. We're talking about industrial control systems, or ICS. These are the digital brains that run our entire world, all the critical infrastructure that we rely on every single day. And this is where things get really tricky. For decades, these systems were completely isolated from the outside world, a strategy called air gapping. But now there's a massive push to connect them to corporate networks, so companies can monitor equipment, predict failures, and just be more efficient. The problem is, the second you build that bridge, you're exposing systems that were designed in a different era to the most hostile environment on Earth, the modern internet. You know, this is where all of our normal ideas about cybersecurity get completely flipped upside down. In a typical office, what's the #1 priority? Confidentiality, keeping secrets secret. But in a power plant? Oh man, the rulebook gets thrown out. The absolute, non-negotiable #1 priority is availability. The plant has to stay running, period. Any security solution that has even a tiny chance of causing a shutdown is just not an option. And that changes everything.
All right, so how have we tried to solve this problem in the past? Well, for years, the standard approach was basically to build a digital fortress using layers and layers of firewalls. Let's see how that's supposed to work. The most common design is called a demilitarized zone, or a DMZ. The best way to think about it is like an airlock in a spaceship. The super-sensitive plant network and the outside corporate network never, ever touch directly. Instead, data gets passed into this middle ground network, this DMZ, where both sides can access it based on a whole bunch of really complex firewall rules. Sounds pretty secure, right? Well, this fortress has some serious cracks in its foundation. And look, this is the fundamental problem with any defense that's based on software. A DMZ needs constant, expensive, expert-level care and feeding. One little mistake in a firewall rule, and there can be thousands of them, can leave a gaping hole. And even if you do everything perfectly, you're still vulnerable to what's called a zero-day attack, a brand new type of hack that no one's ever seen before. You're essentially betting your nation's power grid on perfect code and perfect human oversight 24/7 forever. That's a scary bet.
So if building bigger, more complicated digital walls isn't the answer, what is? Well, this is where a completely different way of thinking comes into play. What if, instead of writing better rules, you could just change the actual physics of the connection itself? Let me introduce you to the data diode, and it does exactly what it sounds like. It's a piece of hardware that acts like a one-way turnstile for your data. Information can flow out, but it is physically impossible for anything, any signal, any attack, any piece of malware to ever travel back in the other direction.
And how it works is just brilliant in its simplicity. Inside most data diodes, there's a fiber optic connection. One circuit board has a tiny laser that sends data as pulses of light. The other board has a light detector that receives those pulses. And that's it. There is no hardware on the receiving end that can send light back. The security isn't guaranteed by some piece of code that could have a bug. It's guaranteed by the laws of physics. You can't hack physics. Okay, so a one-way street for data sounds amazing, perfectly secure, but there's a catch. A big one, actually, when you think about how the internet is built.
Exactly. You're probably thinking, hold on a second, doesn't the internet need two-way communication to work? And you are absolutely right. The fundamental protocol of the internet, TCP/IP, requires a constant back-and-forth conversation, a handshake, just to establish a connection and make sure data arrives safely. If you just shove a one-way device in the middle of that, the whole system just grinds to a halt.
So how do they get around that? Well, with a really clever bit of digital trickery. Use two servers called gateways, one on each side of the diode.
The server on the plant side, the upstream one, basically impersonates the corporate network. It does the whole two-way handshake with the plant systems, collects the data it needs, and then it strips everything else away and sends just the pure data across the one-way diode. Then, on the other side, the downstream server catches that data and serves it up to the real corporate users, handling all of their two-way handshakes. It's genius. Each side thinks it's having a perfectly normal conversation, completely unaware of the unhackable one-way gap in the middle. So that's the theory. Now let's take a look at what a real, state-of-the-art data diode looks like when it's been engineered from the ground up to be truly unhackable.
And this is the most important distinction. You see, a lot of so-called hardware security devices still run a little bit of software on them, something called firmware. And anytime you have software, you have an attack surface. It can have bugs, it needs to be patched, it can be misconfigured. A true hardware-only solution has no CPU, no firmware, no code whatsoever. There is literally nothing to exploit. No patches, no updates, just physics doing its job. This security-first thinking goes into every part of the design. No software means it's completely immune to malware, period. Any configuration that needs to be done happens on a totally separate physical port, so you can't accidentally mess with the actual data path. You can even set up a hardware-based whitelist so the device will only pass data that comes from specific pre-approved machines. Every single layer of security is baked into the physical hardware itself.
And that's really what this is all about. When you're protecting something like the national power grid, you can't afford to be 99.9% sure. You need as close to absolute certainty as you can get. By shifting the security from software, which is made by fallible humans, to a physical principle, which is infallible, you just eliminate entire classes of risk. Human error, bad code, brand new zero-day attacks, they all become irrelevant.
So when you think about it, in this incredibly complex digital world we've built, maybe the strongest shield we have isn't more complex code. Maybe it's just a simple, unchanging law of physics. It really makes you wonder, what other piece of critical infrastructure is next in line for this kind of unhackable physical protection?